This lecture video aims to answer a couple of fundamental questions about how computers work. Namely, what is the architecture of a microcomputer? And how does the operating system fit into this architecture? Specifically, what we try to do is to clarify how computer programs are actually run. So if you remember, from the hardware side, all computer code is run on the CPU. But of course, there is more than that. Not the operating system also needs to be able to start and stop programs. So in order to figure out how it actually does this, we need to look in detail into how programs are actually executed and what does executing a computer program actually mean. Beginning to understand how computer programs and program code works under the bonnet, we have to consider some history. So in the olden days, this would be sometime in the 1950s, 1960s, maybe early 1970s even, computers were not really as commonplace as they are today. I've used the word ubiquitous here, ubiquitous meaning just commonplace every day. Ubiquitous is the opposite of unique. Anyway, so in the olden days, computers were not really as common as they are now. Therefore, meaning that people who worked with computers, that those were scarce professions. And people in those professions were computing experts who really knew what they were doing and really knew how computers work. So people who worked with computers knew exactly how the computer works, how it runs, how it executes program code. Now, skipping ahead a few decades, in modern times, computer systems are much more common. In fact, well, there are slightly more people in the world nowadays than there are computers, but this is likely to change due to the cheap price of manufacturing a microprocessor and the emergence of things like the Internet of Things, IoT, and so forth. So there are much more computers in comparison to 50 years ago. And in addition to having more computers, those computers that we have are much more complex than what they used to be. This is because they all have very complicated software packages. They do complicated things. That means that nowadays people who work with computers are not computing professionals necessarily. They might be anyone. And just anyone do not know how the computer works exactly anymore. I mean, we might have a rough idea about what the components in a computer case do, but it's very rare that most people would actually understand the operation of a microprocessor. In addition, also people who do work with computers know less and less about them because of this complexity, and that's basically due to everything that's fundamental about how computers work or about computer science. All of those details are hidden behind many lower layers of abstractions. So basically, we do not need to understand how the computer works in order to do something productive with it. And if we are IT people or software developers, we still do not need to actually know how the hardware works. So regardless of if you are a IT professional or a layman, we do not really have to understand the bits and bytes and the bolts and nuts of a computer system. This complexity has led to the specialization of some of the IT fields. So only one IT field covers only a small portion of computing. So even a computing professional might not know how everything related to computers work. So someone who's specializing in network technologies might be very proficient in networking, but might not have an idea of how computer devices are engineered. Or a software developer might not have an understanding about computer hardware or networking, but they are very good at producing code. Well, anyway, all these subfields that exist are very niche fields that cover only a small portion of all the computing, all what is in the computing domain. This complexity of computer and software systems is probably best illustrated with a real practical real-life example. So let's take, for example, the Android operating system for mobile phones as something to look at. So you can see here that the Android operating system consists of many layers of different components. So you can see on the bottom right here the lowest stack component, which is the kernel, and herein lives components such as display drivers, USB drivers, camera drivers, all sorts of different drivers for different things, different devices on the mobile device itself. There are also some things related to managing computing resources, such as memory drivers, which you might not at first think is something that needs a driver, but it just happens to have them. Then between kernel and then high-level software, there's something called a hardware abstraction layer, which basically provides services similar to the kernel, but it's a layer that provides these services to the application programs. So if you work as a software developer, you might be able to access these software components. On top of the hardware abstraction layer, there are different libraries, and if you work as a software developer or you take any programming course, apart from the first programming course, then you might see libraries. And libraries are definitely something that programmers work with. So there are different libraries. For example, SQLite is a library for managing a database. WebKit is a library for rendering web pages in a web browser. So all of these important libraries that allow software developers to actually make things work in their application programs. And on top of the libraries, we then have application frameworks and applications themselves. So in practice, these things on these layers, the applications themselves, such as the alarm app or the camera app in your phone, they live on the topmost layer in this software hierarchy. And between the applications and the libraries, there are then some managers which the operating system provides, such as a window manager, for instance. So your operating system, whatever device you're running on, if it's a Windows computer or an Android mobile phone, it must have some sort of mechanism to manage whatever it is you're seeing on the screen. So whenever you switch apps, you're telling the window manager of your operating system to bring something to the foreground and put something else to the background. So these kind of the application framework consists of these kind of managers and providers for those managers. So all in all, there is a lot of content on these levels of the software hierarchy already. What is important to remember from this picture is, even though there is a lot to take in and we're not going to digest this picture, we will come back to it later. The important bit here is that all of these, everything that you see in this picture, is software. All of this is comprised of software code. Everything you see in this picture is some kind of program, some piece of program code that some programmer has implemented. So why is any of this actually important? Why does this need to be in the IT curriculum? Well, the reason is that usually these days, to anyone, including IT students, it's hard to understand how computers actually work. Meaning, we don't often understand the operating principles of computing systems, which is strange because, well, we work with computers almost every day. So what happens is that we are effectively missing a forest from all the trees. This is because typically we study things like programming languages, programming paradigms, something related with information processing, maybe data structures, databases, and all that is very important. All those are important topics, but we seldom stop to think how all of these actually fits into the big picture. How does the entire computer system work? What comes as a surprise to many is that most of these computing principles, how stuff actually works, is not hardware related, but instead it's all software, as we saw in the previous picture. Because software really determines how computers work. But the thing is, software systems are really, really complex. And here we come to this idea, can we even talk about computing or studying computing if we don't understand how computers really work? And this is why these topics on this course are important. On this course module, we are focusing on the operation and working principles of the operating system. Now, the operating system is sort of the glue that holds everything else together. It holds all of the software, all of the hardware working together. So in order to understand how the operating system works to achieve the goal that is implicitly in the name of the course, operating systems and server environments, we have to look at some of the features of the computer architecture as a whole, and some of the features of a software architecture as a whole, in order to understand how the operating or what the operating system actually does. The operating system is special because it really links hardware and software. So we can view the operating system from both hardware and software perspectives. And this is why we talk about both hardware and software. Although the software side of things is more stressed because it is far more important. In general, the operating system is one of the most important components in a computer system, if not the most important. And therefore, in order to understand operating systems, we have to understand computer systems. Now, in order to understand how the computer system works, we have to think of what is it that a computer actually does. What is its main function? So to see this, we should look at the computer architecture as a whole. So what computer architecture means, it means the organization of the computer, and the goal of this whole computing system is simply to execute some programs. That's all the computer system is there to do. As we know from our previous studies in PC technology, the CPU, the main processing unit, can execute very low-level machine code in usually binary code. We call this machine code or binary code. So all of those computer programs that you run are sometimes called binaries because of this. So the CPU only executes binary code, binary machine code. And this is because the CPU is actually not very intelligent. All it can do is process some ones and zeros, binary numbers, and do some computation with them. Now, in contrast, as we know from previous programming courses, usually programs are written using a high-level language and not a very low-level language. I doubt there is anyone in this class who has ever programmed using binary machine code because it doesn't make much sense nowadays. So usually we write programs using a high-level language instead. And this high-level language could be something like C#, JavaScript, Python, Java, Haskell, Racket, Go, or in fact any of the other million other programming languages that exist. What is similar to all of these programming languages is that they are high-level languages. We do not need to write binary code in order to make computer programs. So the main job for the computer and all of this computer architecture is to tie together this very low-level hardware, that is the CPU, and the very high-level computer programs, which are the programs that we write using high-level languages. So in order to illustrate this main task of the computer system, how it translates those high-level programs into something that the CPU can execute, let's consider a very short program, very simple program, such as something that just prints hello world on your screen. So basically the first programming example you often see in programming tutorials. Now this example is deceptively simple because even though at best it can be a one-line program such as something like this, this is a hello world program written in the Ruby language. Similar one-line program here written in the Python programming language. And something that's not exactly a one-line program over here, which is written in the Java language. Now, as said, there are a million different programming languages, and depending on what language you use, these programs look different, but they work in exactly the same way. You write this program code depending on what the programming manual that you are using says how to use those commands in a programming language. And then the computer system does the rest of it, and you see the end result of your program when you run it, and you see the text hello world appear on the screen. Now, depending on what programming language you use, the result can be slightly different, but the working principle is the same. So for example, you can see differences in say object-oriented programming languages versus functional programming languages or procedural programming languages. This first example here is written in a language called LOL code, and I brought this here partly partly as an example of how different programming languages look, and also partly as a joke. So this is not something I have made up. It's actually a existing programming language, which I can prove by showing you the Wikipedia page of this programming language. And as you can see here, a programming language called LOL code actually exists. If you look it up from Wikipedia, you can see a code example pretty similar to the one I showed in the previous slide. And the reason why there is about 1 million different programming languages is because, well, people make their own programming languages depending on what their needs are. So for instance, even though this is more or less a joke language, it just in our context, in the context of our operating systems and server environments class, this just drives the discussion toward there are different programming languages, and they look slightly different, but it really does not matter what high-level programming language you use. What is important is how does that high-level program code get translated into something that the CPU understands. So from the software perspective, the purpose of all of the computing system that you are using is simply to translate this high-level code or something like this into something that the CPU can understand, which is binary, which you can see here. Now, granted, this still doesn't take into account any considerations on the hardware side, so the hardware can remain a mystery for us. But basically, in order to understand how does all of the software in your computer work, you have to understand how this process works here. How does high-level code written inside some high-level language become something that's unreadable to the human eye, but can be executed by a CPU? We will go over this process of how those high-level programs are translated into very low-level machine or binary code that is executable then by the CPU. Before we go into that, or well, we will cover this topic on this and the upcoming lectures. But before we go in detail about, on how it works, let's think of why we are doing this. So, as I said earlier, it is easy for people, including IT people, computing professionals, to forget what the operating principles of computers are. And to understand why this happens, why often people do not consider how the bits and bytes in a computer work, it's because of human nature, the way how we think about things. And this is a phenomenon that's I think the earliest writing on it was in a book by Aristotle called the Third Book of Nicomachean Ethics. So what Aristotle writes in this book is that we deliberate not about ends, but about means. For a doctor does not deliberate whether he shall heal, nor an orator whether he shall persuade, nor a statesman whether he shall produce law and order. They all assume the end and consider how and by what means it is to be attained. So what Aristotle means here is basically we only consider how we are doing things or how stuff works until we have a working solution. And then after we have something that works, for example, a computer, a laptop that you can just buy from the shop, we stop considering how it works, because we at that point we assume the end and just consider how this goal is most easily and best produced. Well, that is the phrasing that Aristotle used at least. So this makes a lot of sense, this philosophy, in the context of this class and these lectures. So it's good to keep in mind this big picture about what we are doing all the time. So right now we are asking the question if all of our computer programs are very high-level code and the computer's processor is only able to operate on very low-level operating machine codes. How does a computer program actually get executed in a computer system? And once we have figured this out, we can move on to the next or at that point we can start deliberating about ends and not means. But so far we are still deliberating about means. Anyway, that's enough philosophy for now. So let's consider what a computer program actually is. In order to understand how it gets translated, we have to look at what it actually is. So a computer program is a collection of code. So it's basically a collection of some program code commands which tell what the programmer wants the computer to do. So it is a collection of commands that govern how some task is completed. This task could be anything. It could be a math problem, such as solving an equation system. It could be something like symbolic computation, like finding and replacing items from text. It could be retrieving a resource from the internet, or oddly enough, it could be the compilation and execution of another computer program. Again, depending on the different programming languages, the language might look different, but usually they contain a small set of similar commands, because at the end of the day, all programming languages pretty much on the whole work about the same way. You usually have some set of inputs, such as reading data from an input device, like a keyboard, like a mouse, or a file. You need some data or some actions from the user in order for the computer program to interact with the human user sitting between the chair and the desktop. You also need some printing or output. So you need to be able to feed data to an output device, such as the screen or a file. Then, in order to process some of the data from the inputs and to the outputs, we might need some mathematical operations. Usually we get sums and square roots and operations like this. Usually, most often programming languages also have some sort of conditional clauses, meaning if-else structures. And finally, repetitions or loop structures. So basically, you repeat a command either exactly the same way or with small changes every iteration of a loop. But those 5 things: inputs, outputs, mathematical operations, if-else or conditional execution, and repetition, basically form the building blocks for every single high-level programming language that exists. Anyway, that's how to break down a programming language. So how to break down a computer program. The example that we looked previously about a hello world program is deceptively simple. If you think about what does it take for this hello world program to actually be executed, what does it take for this program to do something on the CPU? Or what does it take from the CPU to understand what it is that this program code wants to do? Because the program as it is so far, well, that is only text now. Text is just some letters in a text file. And letters themselves are not alive, they're inanimate, meaning they don't actually do anything. So something else has to happen in order for the computer to process that text and to understand what it is that the program and programmer wants to do. This process of figuring out what the different commands in a high level of program code do could be called translating in general. And there are two words, compilation and interpretation, which basically mean different ways of translating computer code. You will probably run into the different or exact meaning of each word when you study some programming language that happens to be either a compiled language or an interpreted language. But this is not important for our discussion right now, so let's just call it translation for now. So this process, translation, because text itself is inanimate, we have to translate into something that is no longer inanimate, or at least is less inanimate. And translation happens in a couple of steps. And the first of those steps is called parsing. Parsing is a process where a program, usually called a parser, tries to figure out the semantics behind the program code. And semantics basically means the meaning of a text. What did the programmer want the computer to do at this line of code? After parsing, the code needs to be translated into something that the CPU can read. This is usually called machine readable or machine code, or machine language or machine instructions. And this process then is called compilation. What is important to understand here is that machine language is an abstraction tool. So machine language is also a way, or machine language is also in a way high-level code as well. Because machine languages, those binary instructions, are a collection of agreed upon binary codes which control what a CPU does. But depending on what CPU you are using, these codes are different. And that's still on the software side. From the hardware perspective, there still has to be some chipset that is able to understand these codes or is able to decode these instructions. In order for a CPU to actually execute some program, we need a program that has been translated or written in this machine language. But after that, we also have to have an actual physical processor, a CPU that supports this machine language, because there are different machine languages depending on the type of a processor. This is usually called an instruction set, so the particular type of machine language that one type of processor supports. And this is implemented in practice by some processor architecture, meaning a type of a processor, and the type is determined by the manufacturer and the general operating principle and physics and wiring in practice. Now, the processor architecture itself is also a agreed upon specification, something set by the manufacturer of the CPU. So this is also just a document. It doesn't actually tell us anything about the actual chipset that will implement this processor architecture. So that is, the chipset basically means how are registers, memory units, buses built and how they operate, and what is the exact binary instruction to store some value into memory, and so forth. And then this physical chipset that implements the processor architecture, this is constructed out of elementary components, elementary logic gates and logic ports. So this integrated package of logic gates, which then are formed from elementary logic gates that consists of logic ports. Logic ports are constructed from switching devices, typically transistors or diodes. And transistors, well, this is where computer science ends and electrical engineering begins. So if we go far enough in this abstraction chain, we can get from the software perspective all the way down to the actual physics that govern how a CPU works and how semiconductors work. But for the purposes of this class, we don't actually need to go this far in. All that I want to say here is that in order for the high-level code to be something that is then executable on the processor, there are many steps, and if you follow those steps, you will get all the way to either electronics and digital electronics, or depending on the computer's type, even quantum physics. But there are many layers to this hierarchy of the computer. These many layers components of the computing system illustrate an idea called an abstraction. To explain what abstractions are, let's consider how do we build these complex computer systems from scratch. If you go to buy a laptop from a store, that laptop computer has to have been manufactured at some point. So how was it built from scratch? How was the first ever computer built? The short answer here is, nowadays, since we already have computers, we can use computers to design other computers. This is a funny quirk of how computing works. So, for example, programming languages are built using other programming languages, and chipsets are designed by using computers utilizing something called hardware description language. So we designed the actual computer hardware using computers. If we consider how terribly complex project building a computing system would be, in terms of what is required by actual physics and electronics components, then all of this complexity would be too much for most people, because at the end, all computers are only comprised of some elementary logic ports. In a similar vein, think of a software program that is run on this terribly complex computer system. How could you manage something like a huge program with hundreds of lines of code? At some point, there is going to be too much complexity. At which exact point, that depends on the programmer and program. Sometimes it's after 10 lines of code, maybe after 50, definitely some point after 100 lines of code. Abstraction is a concept that you run into quickly in programming. So basically what we do in programming is we use functions or methods or procedures, depending on the programming language, what these are called. But we structure code into smaller pieces and try to make code more readable by using these code collections. These code collections, hidden somewhere out of sight, in general are called abstractions. So the idea of abstraction is if we make something, we can then give it an interface or a name and then start using it. So basically the difference between a human and a machine is the ability to look at things from a higher abstraction level. Abstraction basically tells us what something does instead of how it does it. So we can build components on a low level, such as modules which do something. And after completing the build of this module, we can use it to do something indefinitely without having to worry about how it works internally. So for example, in program code, if we have some statement such as a print statement, if we know this statement or piece of code works, we can trust that it will work in the foreseeable future. We don't need to actually know how this command does something, how this print command prints something on screen. Sometimes we have no idea how it works, but we do not need to actually care. We have been told it works because in the manual of this programming language it says this is the way to print characters on screen is by using the print command. An abstraction has an interface which makes it accessible. So the idea with an abstraction is when we use something that is pre-built, such as a software module or a computing device, whoever is using the device uses only this interface, and we do not need to understand the inner workings. And basically, when working with software, all programmers either use interfaces or build interfaces or ask someone else to build them for them. And all in all, what computer architecture is, it's a big collection of interfaces and abstractions. And you can look at this big collection of abstractions either from top down, so that we can see how higher level abstractions reduce or are rewritten using simpler commands, or bottom up, so then we can see how simple components can be built into complex systems. In terms of why computer architecture has to do with translating program code, well, we should look at the big ideas of how computers actually really work and a little bit of history behind that. So the first concept of a programmable computer was coined by Alan Turing in 1936. So basically, in the olden days, or well, prehistoric computers, before this idea of the programmable computer, computers were single purpose only. So whatever task the computer was programmed to solve, that programming had been done on a hardware level, meaning a computer was only able to solve one single problem. Computers were single purpose. Now, Alan Turing's idea of programming computers using electric wiring, electric signals, was the first step toward running different programs, different software on a computer. Conrad Suse's Plan Calcul followed. That was the first idea of transferable code, meaning program code could be transferred between two computers. Then John von Neumann came up with the von Neumann architecture, which is basically the blueprint for all modern computers or CPUs. And then in 1957 we had Fortran, which was the first real relocatable high-level programming language. So all of this development led to the computer not being for single purpose anymore, so you could solve different problems on one computer just by changing the software code that was run on the computer. The really big important idea here is the idea of the programmable computer. So the same hardware can solve different problems using different software code, and all of these both of these ideas basically boil down to the inventions and big ideas of Alan Turing, who invented his theoretical Turing machine. He never really built the programmable computer, but he laid down the groundwork, and then John von Neumann came up with the architecture for a von Neumann machine, which then, as said, is basically the blueprint for every single modern processor that exists nowadays. How the von Neumann architecture depicts a computer? Well, this is actually a very simple model. It consists of 4 different units, or well, 6 if you count the units inside the central processing unit as well, but there are 4 individual different components. There are first of all the input devices, second memory units, third some output devices, and fourth a CPU or a processing unit. So basically the idea that input here is separate from processing, memory, and output. Output being separate from all 3, and most importantly here memory being separate from processing. So the idea here is that in order to be really proficient in changing the software that one computer device, one piece of hardware is able to run, we should separate the memory and processing units of the computer. And this is basically what the von Neumann machine, von Neumann architecture, the big idea here is telling us. So memory, as in program code, so code lives inside the computer memory, and then there is the processor which executes whatever code, and swapping out this memory unit makes the computer do different things. The way to construct a computing device or a von Neumann machine or a very elementary computer, well, if we take a bottom-up approach and look at all of the elementary components that make up the computer architecture, well, from the most bottom level, we start with Boolean algebra. So basically all of the and, or not and operations that we can build with basic logic chips. And it turns out all of the CPU's functionality is actually based on one single Boolean circuit. It's the not and operation, and not and or NAND circuit, which can be used to implement all other logic functions. So all other logic functions can be constructed using the NAND. And this is why the NAND is the elementary building block of a computer. So basically, given that we have a NAND circuit, we can construct everything else from bottom up. So if this was the case, we were handed a NAND circuit, we would be able to build a modern computer. How this would be done is, well, Boolean arithmetic is the set of rules of how Boolean functions. So this elementary algebra can be used as functions to perform calculations. And of course, because Boolean functions are tied to the binary number system, then our logical operations result in either true or false. In base 2, this is enough, meaning we can have some sort of elementary logic in our computer system. Once we have built elementary logic, we can move on to sequential logic. So whereas Boolean algebra is just arithmetic, and arithmetic is just sequential, we can combine different Boolean functions and try to build sequential logic. So if we want to build memory modules, so modules that can store certain values from one point in time to another, we also need some sort of sequential data operations. And in addition to these logic ports, we need some sort of timing mechanism in order to construct functions whose value at one time is something, and then in another point in time, the value of the function is something else. So once we have added a timing device, usually these are in CPUs, processors, these are crystal chips, which are able to resonate at a certain frequency. Then we have basic memory modules, or at least Boolean chips, or elementary logic gates that are able to hold one bit in memory for a certain amount of time. Once we have sequential logic implemented, we can start to build counters and other more complex memory modules by combining these logical circuits and sequential arithmetic devices. So for example, if we are able to build a very simple memory unit such as a flip-flop by combining these n times parallel, we will be able to construct a n-bit register. So then we pretty much have all of the processing hardware that we need in order to execute binary instructions. We still need some sort of high-level architecture for our computer. So this chipset is controlled by using binary signals, those that we feed into these registers, counters, control gates. And what machine language actually is, those binary instructions that the CPU is able to execute, well, that's basically just the system that comprises all these control signals. If we start putting natural language type names onto these control signals, so let's say we had a system such as a chip, let's call this chip just chip, and we had some control ports or control wires here, and for example we had n times these control signals going into this chip. These control signals could of course take values between 1 and 0. So let's say we had some current flowing in these control signal wires. We could start to send actual binary signals to this computer chip, meaning we would have some sequence of binary numbers. And of course, depending on how many binary numbers we tie together, so this would be n. So if n is 64, we would say we have a 64-bit computer or a 64-bit processor, because these are because here n is 64 individual bits. Now, if we started to assign some natural language values to all the possible binary instructions that we had, we could, for instance, say the command or the binary instruction which we have here corresponds to a symbolic machine language or assembly code. That could be, for example, an instruction to store some value into memory. So, for example, this instruction could be store. As an example, this of course is just a made-up example that I just drew onto the presentation. So once you start attaching some natural language names onto binary control codes for our chipset, then we speak of symbolic machine language, or in its technical term, assembly code, which means translating something resembling natural language code into these control signals, which at the end is binary numbers, binary code, which our computer is able to process. So now we have looked on a very high level about how to build a computer, how to build CPU. All you need is some logic ports, you need some timing mechanism, you need some control or you need some wiring to lead to those logic ports. And once you build them into a system of processing and control signals, you pretty much have a CPU built. And the translations of those control signals into some higher level language is then usually called a machine language, and that's the first step in the software hierarchy of a computer. Now, of course, this is not enough as such. I mean, we could program computers using this binary code. We could program computers using this very low level machine language or assembly language. But in practice, we don't do that. So on top of all of this very low level code architecture, on top of these, we use something called an operating system. Now, what the operating system does here, it's basically the piece of software that is in charge of communicating with all of these hardware components beneath the software level. So the operating system just distributes all of the memory processor time of our computer chip. So far I talked only about the CPU, but in practice the CPU also mediates requests toward the memory as well, because the CPU is the interface through which the operating system talks to the rest of the hardware. The operating system also usually in modern computer systems takes care of all the I/O control, so input and output devices, so that a programmer doesn't have to worry about input-output anymore. And then what the operating system also does, which is often forgot, is that system libraries that come with many programming environments, these system libraries are actually not tied to the while they are relevant to the programming language in use, they are actually need to come with the operating system, or at least the operating system has to provide some interface for some programming language libraries to access all of these hardware features. So these operating system comes with some libraries that implement common low-level functions which the processor can do. So for example, as said previously, the CPU is actually pretty dumb. It cannot do a lot of more complex operations. So basically the only thing the CPU knows how to do, it knows how to multiply numbers, it knows how to add numbers together. Some CPUs know how to calculate square roots, but on top of that, basically all the more complicated mathematics operations, those are implemented in software. Then in addition to operating systems, we probably need a programming language. While a programming language is not mandatory for a computer system to boot or anything, in practice we need a programming language or multiple programming languages, compilers and interpreters for those programming languages in order for us to write more software on the computer. And of course, in order for us to write program code, then we also need some data structures and algorithms to implement all of those computer programs. All of the preceding discussion is of course not a guide on how to build a computer system. It's more a really shallow explanation about what computer architecture is and specifically what functional parts there needs to be in a computer system in order for any high-level application to actually run. So of course this is not a guidebook on how to construct a computer from scratch. It's more a story about the different abstraction levels in the computer architecture. Speaking of these abstraction levels, the highest level of abstraction is of course high-level programming. And if we think about abstraction, well, programmers design software and write code on the highest level of abstraction, and even the programming languages themselves, even if they have different levels of abstraction, in terms of or in context of this course, we consider all programming languages to be high level. And programmers basically, or software engineers, count on two basic tools for their work. First of all, the programming language they use, and secondly, all of the system libraries provided by their development environment and the operating system, so that the programs that the programmer writes can access all of the hardware and its features. And speaking of code, the highest level of abstraction in the computer architecture, let's look at the von Neumann architecture once more, and now focus on this program code or computer software. So if we think about how all of the software runs on a computer, and especially how the operating system fits in, all of this is now a discussion about software. So we are not really interested in how certain hardware, such as input-output devices, for example, work. We are a little bit interested in how the CPU works, but that's still not exactly what we are after. But because some software code lives inside the memory units, so whatever happens, whatever logic there is in a computer program, it's all about the code that resides in the memory, and more specifically how that code interacts with those system libraries, those interfaces that the operating system provides to the programmer to interface with the hardware, specifically with the CPU that then acts as a interface to the rest of the computing resources. Of course, the von Neumann architecture is only an idea of how to build a general purpose computer, an idea or a blueprint for a modern computer system. In practice, of course, the architecture of a computer might look a little bit different, maybe something like this. So oftentimes we see the computer system depicted as a collection of software and hardware components. And really, while the idea of the von Neumann architecture separating the processing and logic from the actual program code of the computer, while that is one of the big ideas which makes computers pretty much what they are nowadays, it should be we should remember that it's only a theory concept. It's only a model for practical computer systems. And of course, once we go from conceptual models toward real systems, then things get even more complicated. So if we come back to this picture that we looked at already in the beginning, the Android operating systems software stack, we can see that if we dwell into this software into the software components of a computer architecture, then we will see even more components. Now that we have looked at the computer architecture in general, let's move this presentation toward what an operating system is in general. And let's take the first definition for an operating system. There happens to be multiple definitions for an operating system, and we will get back to that later on. But maybe the first definition for an operating system would be that the operating system is a piece of software that mediates data between other software programs and the driver level or hardware level of the computer's hierarchy or computer architecture. So it mediates data between software and hardware. The operating system also, in general, it does a couple of things. It creates us a platform for multiprocessing, resource allocation, and monitoring of the system and its processes. And in general, we will, or in practice, we will talk about each of these things: processes, threads, and their control, disk management, processor time management, and how to allocate processor time for different software programs. We will get to these concepts later in the course. But for now, just remember that these are basically some of the main tasks that an operating system handles. On a conceptual level, we can categorize some of those main tasks that an operating system handles into three main features. So while the operating system is a pretty complex piece of software, it is a really fundamental part of the computer's architecture, but some of the ideas of how the operating system is constructed are rather simple. And in practice, one of these simple ideas behind operating systems is that they pretty much only have three main tasks or goals or purposes. So an operating system has to do these, or has to solve these three fundamental problems, and those three main fundamental problems or main features are virtualization, concurrency, and persistence. We will get back to these concepts later on in the following lectures, one concept at a time. But in short, virtualization basically means providing a platform for the application programs to run. So in practice, what this means, imagine you download an app on your smartphone. So smartphones exist in they come from different manufacturers, and sometimes they even have different hardware. But the applications that you get from your App Store, or if it's an Android phone, from Google Play, they will work pretty much on any smartphone. And that's one of the things that the operating system, in this case, maybe the Android for Android phones, or iOS for Apple phones, that's what it does. So it provides a platform where all of those applications can run, regardless of the actual hardware that is on the device. And that's a concept that's in short called virtualization. Concurrency is another main task. So concurrency has to do with, well, running multiple application programs at the same time. So presumably you want to be able to run multiple programs at the same time. So for example, you might want to run a word processor and your internet browser at the same time. Or you might want to be able to browse on two sites at the same time, having multiple tabs on your web browser. So that's basically what concurrency means in short. Persistence is the third key main feature. Persistence in practice means some way of storing data, and usually this way is through a file system. So we need to be able to have files on disk which we save in order to save our data. As said, these features will be discussed in more detail further along this course, but these are the main three things to remember in general. And finally, speaking of things needing to be remembered, I will collect one of these slides at the end of each lecture presentation. What do I need to remember from this lesson? So the things to remember, basically, a definition of an operating system. We went through at least one, and we discussed in detail how a computer system works, or what components it consists of. So in there, it is important to understand how the operating system fits, and a definition of operating system is good to have in the back of your mind. We went through computer organization and the blueprint for all modern computers, the von Neumann architecture, or the von Neumann machine. And then there are the three main tasks: virtualization, concurrency, and persistence. This is really the key takeaway from this lecture. And why it's the key takeaway? Well, basically, in computer systems, if you can figure out how to do these tasks, these main tasks, all of the rest is pretty much trivial. These are the big important problems to solve. Modern operating systems solve these problems pretty well. And in the next lectures, we will be looking at how operating systems actually solve those big problems, how they accomplish this feat.